So let's pick up with another example. Let's work in a distributed load on this one. Example. Now this one we're going to use a fixed support. Right? So a fixed support. Well, actually, before we work the example, let's talk about the fixed support. So a fixed support would be some structure that is basically concreted in or welded in or very, very firmly attached. A fixed support is going to prevent rotation and motion. If it prevents rotation, that means this is a moment reaction. And if it prevents motion, that means it's a force reaction. Now remember back over here, these guys, both the pin and the rocker, so the pin doesn't prevent rotation. Rotation can occur. The rocker doesn't stop rotation. Rotation can occur. It doesn't stop motion in this direction. It only stops motion into the surface. So I have an unknown force perpendicular to the surface. But again, with the pin, it stops motion in both the X direction and the Y direction, but it doesn't stop rotation. The fixed support, on the other hand, prevents rotation. I don't have a good example of a fixed support here. I mean, it would be something like, again, something either concreted or welded in to where there's no way to move it, period. Either causing rotation or trying, if I try to pull it in the X direction, it won't come out. If I try to push it up in the Y direction, it won't come off. And if I try to rotate it, it won't rotate. That's a fixed support. So if I draw that in free body diagram form, I'm going to have a force in the X direction, if this is point A. Right? I'm going to have a force in the X direction because it can't move in the X direction. I'm going to have a force in the Y direction because it can't move in the Y direction. But again, it won't rotate. So I also have a couple moment reaction about point A. So I have three unknowns. And I have three unknowns. Now normally I would do a component in the X and a component in the Y. You can do a force, an unknown A force at an unknown angle. That would be fine. That would still be three unknowns when you add the couple reaction in there, or the couple moment reaction in there. So again, in 2 dimensions, a fixed support has three unknowns. And then the last one, we've already seen. The last one would be at least the most common one. Now you'll encounter some others. There are several, like we talked about last time, that you'll find a table. You should find a table in your statics book showing all kinds of different reactions. These are just kind of the 4 most common ones. But you could also have a cable, which we've already seen in chapter 3. And a cable, then, if I attach a cable to some structure here, right, when I draw that in free body diagram format, again, the cable can only provide tension in the direction of the cable. So if this is angle theta, that tension is going to be at angle theta. So the direction of the cable, the direction of the tension is known. The only thing that's not known is the tension. But again, here you've got an unknown direction and magnitude or XY components, and you've got a reaction moment. So in 2D, this is one of the few times you're going to have a reaction moment. There's some other kind of more exotic fittings, but that's kind of the most common one. All right, let's look at a fixed support example. So L8, and I've got this is page 6 of something. So again, example, and then I've got, let's just say I've got a wall, kind of like I drew the fixed support example last time. I've got a 6-foot pole coming out of this wall. Okay, and then halfway through, I've got kind of a trapezoidal load pushing up from the bottom. So it's not a square, it's not a triangle, it's somewhere in between. So I have this distributed load that right here at the kind of the big end is at 30 pound per foot. And at the small end, it goes all the way down to 10 pound per foot. So it's a linear decrease. As you get further and further along, it gets less and less, but it's distributed along this entire length here. Now that is a 3 foot span to where it starts, and another 3 foot span to the end of it. Okay. Then I've got, so this is what I would suggest. What I like to do with this normally, now you can say that this is, you can write an equation for this, right? So the equation here, this is, you're going 20, you're increasing 20 pound per foot, or I guess decreasing 20 pound per foot over a span of 3 foot. So you would have, your rise would be, I guess, a 20 pound per foot over a distance of 3 foot. So the slope would be 20/3, and you would have a y-intercept out here of, I don't know, whatever this goes out, so another 20, so you'd be down here at 50 would be your y-intercept or at x is equal to 0. So all that to say, you would have an equation here of 20 over 3x minus 50 basically would be the equation for the line here. And you could integrate, you could do the calculus and actually integrate that from 3 foot to 6 foot out on x and do the calculus for this. I don't really like to do that because this works just as good. I could say, you know what, I've got a rectangular 10 pound per foot rectangular load, and then after that I've got a triangular load on top of that that goes from 0 here up to 20 pounds per foot. And both of them are applied a span of 3 feet out here at the end of this beam. And then this guy is, I've got AX, AY, and then I've got a reaction moment there at A. And what the heck are we looking for, Steve? This is find reactions at A, that being this fixed support there. So we can do this. Now, what I like to do, a lot of times, there are very few times I like to leave a distributed load distributed on a free body diagram. What I normally like to do is say, this would be my final version of a free body diagram. This would be the easy thing to write equilibrium equations from. Let's start it out there. Kind of keep it even with these diagrams. I guess it needs to come further out. I apologize. Keep it even with these guys. Okay, so ignore these lines in there. So we've got over here at point A, I've got AX, AY, and I've got this moment reaction at A. And then I've got this 10 pound per foot load here over a distance of 3 foot. So 10 pound per foot over a distance of 3 foot. That means I've got, and its middle is going to be right in here. So I've got 10 pounds times 3 foot, that is 30 pounds. That would be the area of that rectangle. 30 times 10, 30 pound per foot times 3 foot, 10 pound per foot times 3 foot gives me 30 pounds. That is going to be a distance of 1.5 foot from the edge here. Okay, then I've got this triangle here. Now the triangle is 20 pounds over a span of 3 foot. Remember, the area of the triangle is going to be 1/2 this 20 times this 3. So 1/2 20 times 3 is also going to be, it's half of 60. That's going to be also 30 pounds. Its center is going to be right in here somewhere. So I'm going to apply that force at the center. Now again, that is 1/2 of 20 times 30. 1/2 of 20 times 3, that's 30 pounds. And its distance, so it's 3 foot here. The center is going to be 2/3 from this end or 1/3 from this end. So it's going to be 1 foot here or 2 foot here, whichever way you want to go with it. I might say it's 1 foot from here. Right, so if it's 1 foot from here, that means it's 3 foot to the edge of this triangle, and then 1 more foot into where that force is. So that means it's 3 foot plus 1 more foot to where that triangle is. That is 4 feet. The whole thing should be 6 foot, meaning this span here is 0.5 feet. Right, so 4 foot to the center of this triangle, 3 foot plus 1 to the center of this triangle. And then again, this guy is half a foot from the edge, or I'm sorry, 1.5 foot from the edge, or 1.5 foot from this 3 foot there. So 4.5 feet from the edge of A. Okay. All right, so that's my free body diagram. I should be able to apply equilibrium now. 3 unknowns here. Sum of forces in the x direction is always, your sum of forces in equilibrium is always going to be 0. We add up all the x direction forces, AX. That's it. That guy's 0. That one's known. That one's easy. Those are the easy equations, right? Give me those all day. All right. Sum of forces in the y direction. That's going to also add up to be 0, and I've got AY plus 30 pounds plus another 30 pounds. I've got 2 30-pound loads, both going in the positive y direction. So AY is actually going to be minus 60 pounds. When I solve that equation out, AY is actually going to end up being minus 60 pounds. All right, pause here and see if you can write the moment equation. I'm going to write a moment about A. Let's see if you can write a moment, any moment equation, but I'm going to write a moment equation about A, set it equal to 0. See if you can write that out. All right, you got it there? Okay. Now, here's what we got to do. We've got, from point A, I've got a force here, and it is pushing in the counterclockwise or positive direction. I've got 30 pounds at a distance of, this one is 4 foot, at a distance of 4 foot. And I've got another 30 pounds here at a distance of 4.5 foot, also counterclockwise, 30 pounds at a distance of 4.5 feet. And then finally, I've got another moment here. This guy is just a moment. It doesn't matter where it's located. It just gets applied in the equation. It is currently drawn counterclockwise. I drew it positive. You could have looked at this and said, Steve, it needs to be clockwise to counteract these two. I wouldn't have argued with you. That would have been fine. Go ahead and calculate that out. Pause here, calculate that out, and see if you can get the number. I've written here that that is, because it's drawn counterclockwise, it actually needs to be clockwise. I have written down here 255 pound-feet. See if that's what you got. And there we go. And that makes a nice stopping place. It's kind of it's a good amount for most of a 75-minute lecture. I think we'll stop there and we'll pick it up next time. But this gets you started into Chapter 5 in the Hibbeler text. So you should be able to start working Chapter 5 problems now.